So there was a question earlier about, acknowledging in the first session what happens when everything gets acknowledged and what happens if all the acknowledgments goes missing. And then we talked about this concept of retransmission timeout. Okay, I'm going to show you an example of what happens when a packet goes missing, the acknowledgments goes missing, or a quick way to find out if this is a access list or a firewall or a random packet loss. So I'm going to kind of give you a quick hint on how to figure that out. So if I scroll down here, you see symptoms of packet loss, right? You see duplicate acknowledgments and you see retransmissions, okay? And then you see a spurious retransmission. What's that about? Well, actually, Jasper has a blog post on what spurious retransmission means. But the idea here is that an acknowledgement happens because you sent it some data and something happened and I need to retransmit that data, right? Everybody get that, right? So there's a concept of what's called a fast retransmission. When you tell me 4 times in a row that you didn't get a particular segment, then I'm going to immediately retransmit, and there is almost no penalty to that. All right? So when you have a fast retransmission, the performance is almost nil. There is almost 0 penalty to that retransmission, unless there's an issue with complete stoppage of that transmission. Okay? And so the reason why I bring that up is because if I click on this delta column and I go down, you'll see this behavior where I'm doing a retransmission, and you notice that it takes 1 second, 2 seconds, 4 seconds, 8 seconds, 16 seconds. And it's actually, if you go through the sequence number, it's all the same. Notice the sequence number here, 70 and 24 are all the same. So as I click down, take a look down here, sequence number 70 and 24, it's all the same packet. But why does it double in time? This is the back off that TCP uses. Okay? Why does TCP use a back off to retransmit? Why does he wait twice as long to retransmit, twice as long to retransmit? This is the flow control part of TCP. TCP is saying, hey, there must be a problem. It must really be congested. I'm not going to make my problem worse by blasting you with more data. I'm going to throttle down, and I'm going to wait, okay? So in the States, when you go on the freeway, on the on-ramp, there's actually a meter, right? Green light, red light, because they don't want a bunch of people getting into the freeway causing congestion. So they meter how many people can get on the road from the on-ramp to the freeway. TCP is doing similar things. In this particular example, it's interesting because the outcome is more interesting than the packet analysis itself. If you notice, okay, there's a SYN-SYNAC, so the TCP socket gets established. The TCP connection happened. So we can immediately rule out an access list. Because if there was an access list blocking this traffic, it wouldn't have been SYN-SYNAC ACK. Right? We can all agree on that. And then there's, some transfer that happens here. So when you see an example like this where there's initial traffic that seems to be working okay from a TCP socket level and all of a sudden it stops, there's only 3 things that can do this. So what I'm saying is you can quickly rule out the vast majority of your network and concentrate on 3 things, 3 devices that can do this. That's the firewall, a proxy, and steelheads, or any kind of optimization, the inferior optimization that you might have if it's not a steelhead. That's my commercial number 2. Because only proxies, firewalls, and by firewalls I'm including IDS, IPS in there too, okay? So only firewalls, proxies, and steelheads munge the data that you're talking about. And when things go wrong inside there, things like this can happen. So when you see a behavior where TCP connection happens and all of a sudden you see this back off happening, this means that this packet and this data never reached the sender. And because the receiver. And because it never reached the receiver cannot acknowledge what he didn't receive. Okay, so think about it as I explain these concepts. If I sent this to you and you never received it, how are you going to acknowledge me? You never received anything. But I know this communication was working because up here you were acknowledging me. So this is a case where this was a firewall problem that stopped this traffic from going through. Okay? So this is just a quick way of saying when you see connections open and some traffic happens and all of a sudden it stops and you see this binary back off of 2, 4, 8, 16 for the same segment, it's firewall, steelheads, or proxies. That's it. Routers can't do this. Routers cannot cause this problem. Okay? Any questions? Yes?
The router will be rebooted in this time for every instance.
If
it doesn't react gateway in any way.
I'm sorry.
If the router will be rebooted during this time.
Okay. So that's the. So what happens if a router gets rebooted during this time? What happens if a router gets rebooted during this time? The correct answer is, because you have a redundant router, it should immediately. You might see a little burp, a little retransmission, but then it should immediately go. If you don't, you're exactly right, but then you have SNMP monitoring for that, right? So that's when you say, oh, okay, you're not. So I'll give you a quick example of what happened to me. I was giving a training in Japan for a financial company, and I was tracking retransmissions, and I'll show you that maybe in just later. And I said, you know, because I can track retransmissions, if the retransmission goes sky high all of a sudden, you have massive problem. And everybody's like, yeah, that makes sense, right? Retransmission is normal. Every network has retransmissions, I guarantee it, because nobody builds their network to their peak capacity except for trading floors. Okay, outside of trading floor, nobody builds a network to peak capacity. So I said, keep an eye on the retransmission, and when it goes sky high, you'll see that there's a problem, and everybody got it. And then as I was walking away back to my computer, everybody in the audience went, oh! And I said, what? And I looked, and the retransmission rate went sky high. And I'd be lying if a little bit of me didn't say, all right, this is awesome. Because it was almost perfect timing, as if I rebooted a core router. And that's what happened. A core router in a network rebooted, and it took 45 seconds for those retransmissions to go away. I just said, the redundant router should pick up immediately, and it didn't. Why? Any guesses? Anybody? So there was some kind of a timeout issue, right? That's a good answer. But here's I'll get to the chase of it because, you know, we're on a limited time. In modern networking, there's two ways routing protocols let everybody else know that there's a problem. When an interface goes down, I do a flash update. Whether it's OSPF or BGP, I withdraw the routes. There's everything about, you know, speed, speed, speed. You can even make OSPF sub-second if you like. This problem was twofold. One, there was a soft failure that occurred. Soft failure meaning the router didn't reboot, it just stopped forwarding packets. And that's the biggest pain in the ass to troubleshoot in the world because SNMP is going to lie to you. All your monitoring is going to lie to you because it's almost dead. Okay? The other one is timers, and timers basic, right? So for BGP, timer basic 416 means 4 keep alive, 16 seconds later, reconverge. And you can tune that down, 2 and 8. Okay, 1 and 4. The problem with tuning it down too aggressively is that you can fail over when the failure didn't occur. All right, but this is not the routing class, so I'm gonna pull myself back from going too deep into the routing side. Any questions about that? I'll show you how to monitor some of that towards the end if we have time. Okay, so the other part that I didn't get to this morning in the basic session was, how do I know what that MTU is? All right, we talked about MTU and MSS. How do you know? Because there's actually a mechanism that tells you what it should be. Okay? And that's in the form of ICMP. So this trace itself is not that, I'm not going to go into what the problem with this is. I just wanted to show you that they thought of everything. There's an ICMP type 3 code 4, which is fragmentation required, but you told me not to fragment, okay? So what that means is if I look at any other packet here at the IP level, it'll say, it's okay, hold on. Actually, let's just get to here first. All right. So this is an ICMP type 3 code 4 that says fragmentation is required, but you said don't fragment. So we have a don't fragment fit, a bit that every packet goes out with to do exactly this, which is path MTU discovery. So along the path, some router has a smaller MTU because there are IPsec headers, there's a GRE header, or there's some other header that needs to make the MTU and MSS as a result smaller. So the mechanism in doing that is this. So let me show you what this looks like. So the conversation is between this 192.168.231 to some address, okay? That's the original conversation. The reason why there's an ICMP here is because some router along the path, any random router along the path sent you this message that said, hey, type 3 code 4, destination unreachable, fragmentation needed, and the next top is 1430. I know you wanted 1460, but I'm telling you, because I'm the router, I look at this interface, the MTU is going to be 1430, adjust accordingly. So this is a way of routers along the way telling you, don't use 1460, use 1430. And by the way, just for your reference, this is the original source destination that caused me, the router, to send you this alert. Okay? So why does ICMP include the source destination? Because the way path MTU discovery works is when you, the sender, if I am 192.168.121.231, okay, and I receive this message from some router along the path, my job in my routing table, and you can see this with netstat command, is to build a host route for this destination and make the next top size 1430 MTU. Okay? So this is how path MTU discovery works. So that as a sender involved in this conversation, I now know anytime I want to talk to this 192.168.101.152, the original destination, I am not going to send it 1460 MTU. I'm going to send it just 1430. Okay? Yes, question.
Sometimes it happened to us that along the path, any router, it could be filtered the ICMP messages totally, not only the ICMP echo and request messages, but all the ICMP.
Yes.
Does it mean that PMTU does still work and will hop on to the next router then? Or
Okay, so let me answer that. So the question was somewhere along the way, a router filters or doesn't answer any ICMP messages. That's wrong. At the very least, you can say I'm going to block ICMP ping to protect myself, but you should open up ICMP type 3 code 4 because otherwise it's up to you, the router, to make sure you adjust the MSS. So there's a command for that, okay? Which is TCP MSS adjust. The philosophically why I'm against it is because now you're asking a router, which doesn't have a general compute CPU on there, to reach into every TCP packet and look at the SYN/SYN-ACK, go into the MSS and modify that. The router has to do that now, okay? So that's why I'm against it. So ICMP type 3 code 4 is designed to do that. The second part of that question was, does some router beyond that give you that ICMP message? And the answer is no, because the original big size never makes it past this router, so there isn't another router behind it who can send that message. Number 3, Cisco and all modern day routers have CPP, control plane protection. It does things like, I will not answer 50,000 ping that you just sent to me to protect the control plane. So it rate limits by default, every router nowadays rate limits ICMP, including type 3 code 4 messages. And that's bad if you have a load balancer with a VIP and a boatload of clients that come in through a common head-end router. So imagine a head-end router that services 1,000 users, 1,000 branch users, okay? And you have a common workflow where you do a download at middle of the night. Everybody logs in around 8 o'clock, okay? And you have all this traffic, 1,000 traffic coming in to one head-end router, going to one virtual IP, a VIP address, and the router has control plane protection for ICMP type 3 code 4. So typically it'll do 4 per second. Okay? Which means the first 4 within a second window gets that ICMP message saying, make it smaller, but everybody else is screwed. And you have random black holing. And what happens? People get tired, they close the browser, come back, and in that, so now 10 seconds have elapsed, so now the path MTU discovery works. Okay? So there's a command called IP ICMP rate limit DF for do not fragment, and make it instead of every, you can rate limit it to say answer this every 100 milliseconds, for example. So there's actually a router command that you can use to fine tune the ICMP type 3 code 4 messages specifically. Okay? And in fact, internally, that's a best design practice so that you don't have this mysterious black holing of traffic. Okay? Good? All right. So that's how the ICMP works. And let's look at my notes here so I don't get the code word of fish and wander off the reservation too much. All right, so let's look at some interesting trace files where there's slowness. And I'm going to look at external app slow. This is a real-world use case where a user complained the network is slow, horrifically slow, and it must be the network. And now we all can say it's not the network, but you have to prove yourself innocent. So what is your mean time to innocence? So we said, let me see the packet, and sure enough, what's the first thing that jumps out at you? Without even going through my usual workflow, because there's a video for that. I'm not even going to show you that workflow for now. I've actually highlighted that. I didn't mean to, but I highlighted it. Just yeah, 16-second delta. I honestly didn't mean to highlight that, but 16-second delta. So whose fault is it? How do you figure out whose fault this is? So let me show you a quick workflow on how to identify whose fault is this. So the first one is easy, okay? TCP handshake, and you can look at there are no options here. This is a plain Jane ICMP, and you see here that there are no options either, okay? Which makes you go, because modern day servers should have selective acknowledgement, window scaling, etc. That's your first clue where you go, why aren't you offering up these high-speed, newfangled TCP options, selective acknowledgement timestamps, and etc. Okay? So that's file it away. Where am I capturing? I'm capturing from 192.168.1.1 because I sent a SYN, some time passed, I saw the SYNAC, and I immediately see acknowledgement. So I'm capturing at where? The 10 dot guy? 192 guy or 10 dot guy? Where am I capturing at? Yep. Okay. So based on the handshake, chances are I'm capturing from 10.10. There's another thing that you can use, which is, am I really capturing from the 10.host? No, I'm not. I'm close to 10 dot, but I'm not capturing from 10.host. Why? Look at the MAC address. Source destination is Cisco. So this is not a Cisco router talking to and doing an iOS update or doing HTTP or doing IPSLA or anything like that. So I am very close to 10 dot, but I am not at the 10 dot itself, because otherwise a source MAC address wouldn't be Cisco, all right? But I know I'm very close to it. So my handshake happens, that's good. And then what happens? I send some data. Oh, sorry, down here. Oh, actually, I was completely wrong, because I wasn't even looking at the SYN-SYNAC ACK. I was doing that just to trick you, to make sure you're on your toes. It's actually, I'm close to 192.168.1.1. And in this case, but the argument still holds, right, which is Cisco source destination MAC address. But I'm at the 192.168 because I see 192.168, I see some delay, and immediately I see an acknowledgement for that SYN, so I'm close to 192.168.1.1. But again, because of the Cisco MAC addresses, I'm close to it, but not immediately there. So now, the conversation starts, because I'm starting with sequence number of 1, and I'm sending 411 passengers, okay? And I have the next expected sequence number 412. So this is the beginning of my transmission. Remember, sequence number plus the amount that you sent equals the next expected sequence number, which is also the acknowledgement number. So I'm expecting, I sent you 411, and the other guy says, yeah, go ahead and send 411, next expected sequence number of 412, and sure enough, the other guy says, yep, go ahead and acknowledge 412, you're good. Okay, everybody got that? So are there any outstanding data on the wire? No, there are no outstanding data on the wire, because this is a pretty simple trace. I sent you 411 bytes of data. You haven't sent me anything yet. 10 dot has not sent the 192.168 any data whatsoever, other than the SYN-SYNAC ACK. So 192.168 sent data here. The 10 dot guy says, I got it. And it took 140 milliseconds, which is pretty much the round trip time. So the 10 dot guy immediately said, I got the 411 passengers. And nothing for 16 seconds. And 16, almost 17 seconds later, he sends me 41 bytes of some data. Okay? So who's at fault? The 10 dot guy. Okay? Reasonable. What if there's something upstream that caused this to happen? And that's exactly what the vendor said. And the vendor said, hey, you're going through the internet, you're connecting to me through the internet, how do you know it's not the internet? For a couple of reasons. One, there is no router in the world that can hold a packet for 16 seconds. There isn't. I can go around the world 400 times, okay? It takes less than that to go to the moon and back, for example. Okay? So, and it actually takes 500 milliseconds to go to low Earth orbit and then back. So 16 seconds is an eternity. Okay? But what if this was as a result of packet loss? And the other guy is trying to retransmit to me. What if my firewall was busy and was dropping packets and was not allowing these 10.10.10 to come in, and the vendor kept having to retransmit? What if this is a retransmission timeout? The vendor sent this, okay? So the vendor sent this 17 seconds ago. And my firewall stopped it from happening, and the vendor kept trying and trying and trying. And after 16 back off seconds later, it finally let it through. Okay? That's what the vendor told me. Because the vendor knew enough packet analysis to say, how do you know? How do we know? Is there a way to know for beyond a shadow of a doubt that this is not a firewall along the way blocking it, and then okay, let's take a look at the TTL. TTL is time to live. Okay? Initially, when the RFP was written, we had what's called IMPs, Internet Message, I forgot what the P stood for. Okay? And the original TTL's job was to calculate per hop latency. So time to live was exactly that. And then they realized, well, this is stupid. I'm a router handling all these traffic. Trying to maintain state of how long these are taking is taking too long, too complicated, so let's just call it 1. Okay, we'll start with some number like 64, and I'll just decrement by 1. So it was actually a second how long it was to traverse these networks, and then it became just every router decrements the number by 1. So you can come up to here and say, all right, and TCP, that TTL number is in the IP header. Okay? So, and again, another way of fingerprinting it. So time to live is 62, which means, remember I said this is Cisco source and destination MAC? I'm 2 hops away from this client, because chances are he's using a client with 64 TTL. Pretty old operating system, right? We can all agree on it, because modern day operating systems don't start with 64. Let's see what the server sent. Their server sent a TTL of 44. So likely he started out at 64 and it took 20 or so hops along the way to get to me. Not unreasonable. 20 hops is nothing these days, okay? Now, did it start at 128 and it took over, 80 hops? Possible, but probably not likely. It's possible. I don't know for a fact, okay? So in this case, TTL doesn't help me as much. It's a good clue, though, because let's look at this guy, and his TTL is 44, and the other one was 44. So the one thing I can rule out is there was this massive going around the world a different path that eats up more TTL before it got to me. So this wasn't a reroute condition. So TTL helps me in ruling out a reroute where I took a much, much longer path. Okay, rule that out. So how did I prove, how did I say, suck it, because this is 100% on you? How did I prove that? And that is IP ID. Okay, every packet that goes out gets stamped with IP identification. It's not required. It can increment by 2, it can increment by 1, or it can be 0. You don't need it unless you fragment the packet. That's the only time you need IP ID. But most servers increment by 1, okay? Unless that server is very, very busy and is talking to multiple clients, then you might see an IP ID of 10,000 and 14,000, okay? That means between those 2 packets coming to you as the client, the server was busy talking to or generated 3,999 other packets for somebody else but you. Okay, so it's another way of gauging how busy that server is. Okay, and before I get called out on it, that statement is actually false, because the IP ID is only 2 bytes. So you can actually wrap around. Okay, it's not a big, so you can actually wrap around 3 times, which means it's much, much busier than you thought. In this case, though, all I had to do was say, hold on a second. It's true that my firewall could have momentarily stopped this traffic to inspect the content, and it took 16 seconds. It could happen. That's why I have an IPS IDS stack. But the problem with this is that this packet, where you acknowledge that you got my packet, had an IP ID of 17048. And 16 seconds later, what is it? 48, 49. You see this IP ID? Okay. 48, 49. It incremented by 1. What do you think my next question was to the vendor? Remember, this is me talking to a B2B partner that I paid for, or the business did, and the business complained of network slowness, looked at the packet trace file, sure enough, there's 16 seconds. I was like, oh my God, that's ugly, okay? And after that, it seems to be okay, right? You can see here, it's not too bad. This is the initial double click. Oh, network is so slow. So what do you think my next question was to the vendor when I saw this? Other than showing, hey, there was no packet loss, internet is not responsible, right? You didn't try to send it 5, 6, 7 times because my firewall was blocking it. I know that because if this was a retransmission, I would have expected the IP ID to increment. But what's suspicious about a commercial online transaction and this statement of IP ID incrementing by 1?
How many clients are on the network?
Exactly. My question was, are you about to go out of business? Because in 16 seconds, which is an eternity in the networking terms, I'm the only customer you serviced? How can that be? And they went, oh yeah, you're right. How is it possible that in 16 seconds, a commercial online application only serviced me? And they said, you're right, that doesn't, we have a lot of customers. And I said, you don't, because in 16 seconds, you only service me. And then they said, oh, wait a minute, I see what's happening. You went to our development server. Well, I didn't, because I'm the router. I'll just go wherever the packet says that it needs to go. They were testing the service using a development server, and they forgot to change to production IP DNS name. Okay? So this was, while it had the data, it was a slow, decrepit server that no one pays attention to, and that was a problem. Okay? So this is one of those cases where without a packet trace, it might have been very hard to prove otherwise. Okay? But using the IP ID, I was able to rule out a whole bunch of issues, potential firewall blocking, potential reroute issues, etc., and say, hey, this is 100% on you. Remember the first thing we did was, are there any outstanding data on the wire? Answer is no. Then whoever speaks first is responsible for that slowness. So here's a general rule of thumb you can remember. If there are no outstanding data on the wire, and everybody's quiet, and all of a sudden somebody speaks up, that's the guy responsible for the slowness. Okay? Because without prompting, that guy decided to send me something, which means the server that sent me something was thinking about it before he was sending it to me. Okay? And another thing you can do is you can use a IP ID to fingerprint how busy that remote server is. Okay? By looking at the IP ID going up by 1,000, 2,000, 4,000. Now, it can be, 64,000 more because it could wrap around, but you'll get a feel for it the more traces that you look at. Okay, any questions on that so far? So that's a way of using IP ID to figure out, A, why were you so quiet for 16 seconds, and B, there was no packet loss because the IP ID was the same. Okay? Good? Yes?
Couldn't this be also an application protocol issue? Because we do not know which application they drive, and so we requested something from the application.
That's right.
Somehow there is an I/O error with the hard disk, something else,
Mm-hmm.
and it took a long time here.
Yep, okay.
I think the answer comes.
Right, so here's the problem. You can, and I always use this phrase, and I think it's spot on, I should trademark it. You're trying to get a murder conviction without a body. Why is that hard to do? Why is it historically hard to get a murder conviction without a body? Because in the United States, the standard is you have to prove beyond a reasonable doubt, and that's the only way you get convicted. Okay? So getting a murder conviction without a body is hard because the defense can say, he went to Trinidad, prove me that he didn't. The guy's not dead, he's in Jamaica, he's in Kiev, he's in Moscow, he's in Thailand. Prove me that he's not. And you can't. That's why it's hard to get a conviction for murder without a body. In the world we live in, very rarely do you get a smoking gun. You have to have what's called the preponderance of evidence that suggests that it's an application issue. And we'll talk about some other hints in this trace file not this trace file, but other examples on how to get those examples. Okay? Any questions about that? It's almost like I paid you because that's the next example that I'm going to show you. And this is a slow transfer. So this is, again, doing a transfer, and it's slow, and the network is to be blamed. Okay? All right, so let's take a look. So the one, the synact doesn't even matter. What's the one thing that you can tell about this trace file as I scroll down? It's not too bad, because it's using full size, right? There's all these full size packets here. Seems like it's pretty decent. And yet they're complaining about slowness. Okay, why is that? We'll see. What other things do you notice about this, this trace file just by looking at it? What are some of the things that?
Acts are not every 2 packets.
Okay, so you'll notice that the act's not every 2 packets, which in my first session I said you must act every 2 packets. However, let me just address that and nip that in the bud right away. It depends on where you're capturing from, okay? The reason why it matters is because think about where you're capturing from. If you're capturing from the guy that's sending the act out, meaning, let's say, for the sake of argument, that I am capturing from 192.168.1.100. If I'm capturing from here, I would see 2 packets received, immediate acknowledgement go out. Because I'm very, very close to the 192.168.100 guy. Okay? However, if I'm sending the data, I'm going to send you a boatload of data as much as your Windows, the receive buffer allows me to. So if I have a 64,000 byte window, I can send 64,000 bytes of data, however many packets that is, before I see a single ACK. Okay? So you have to look at in terms of perspective and where am I capturing because it looks very different. If I'm the sender, huge packet train, no ACKs, and then the ACKs start to come in. If I'm on the receiver side, I see a huge number of packets come in, but every 2 packets I'll ACK. Okay? So that's why, but it's a good observation about, the acknowledgement being different. Okay? What else? It's SSH, right? Because it tells you right there. Okay? And also because this port number, every once in a while you'll see port number here, 22. So this is secure copy. All right? And how bad is it? Is it good? Is it bad? I don't know. One way to look at it is you can just look at things like IO graph. There's Stevens graph, TCP trace. And I think it was Kerry who said, oh, why do people use Stevens graph when there's a TCP trace, which gives you a lot more data? It's because you're old. And what Kerry meant by that is people like me, when we started, Stevens graph was all we had. Okay, now there are much better graphs, but it's very hard for me to break my habit because I'm used to my way. And so I always go to Stevens graph, and then, I can use TCP trace graph, but it's just muscle memory. So what this is showing is it's just over time how much data I'm transmitting. The steeper the slope, the better it is. And when you first look at it, it doesn't look half bad. Like, hey, there's a 45-degree angle. What's the problem there? But then when you zoom in, you start to see the problem. And what's this problem? Every one of these are transfers that are happening. And if I click on it, in the background, you can see packet numbers changing. And then, so what this is showing you there is that the sender, it has huge amount of data to send, waits, gets some of the acknowledgements, and then he transmits a little bit more because he cleared out this buffer space. He transmits more. He waits, sends more, waits, sends a little more, waits, sends. So this is a classic behavior of maybe TCP window size must be at fault. Remember what I said. You can only send 1 full window size per transfer, right? You can only send one full window size per transfer. I know this is not the TCP window size. Why? Exactly. Chris is going like this, okay? He's not telling me like you're talking too much. He's saying the bars are different sizes. If TCP window size was the limiting factor, and let's say this is the full TCP window size, you should see full window size, nothing, full window size, nothing, full window size, nothing, full window size. If TCP window was 64,000, you should see 64,000 bytes worth of data, 64, 64, if that was the limiting factor. And it's not. Clearly it's not, because these here, that's not the TCP window size. That's not the TCP window size, okay? Just a couple things that you can clue into as you visually look at this, right? So what is the problem here? What's going on? And there is a pattern here, if you notice here, right? Full, small, 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 full, small, 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 full, small, 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 more small, full, small, 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 full, bigger. So there is some pattern here that's happening, and it's repeating. So if I look at one of these guys, and it doesn't matter which one, let's just use this guy, for example. It's a full size, it's a start of a packet train, obviously because the graph showed the amount of data being sent, and it showed all these data being sent before there was quiet time, and you can actually come down here and measure the delta, and you'll see a bigger gap before it continues on. So what could be at fault? Is it TCP window size problem? Is there a way to know if it's a TCP window size? I don't have a sense and act. The only time the window size is positively identified is during the sense and act, because there's a multiplier called window scaling. So if it was a TCP window size problem, you would see things like window size of 0, meaning I can't accept this data anymore, okay? So that's one clue that you would be looking at. And here we don't see that. What's the other way to look at it? And if this was a really advanced session, I would go into heuristically how you can determine the send and the receive. They both matter, okay? The window size matters as a sender and as a receiver, okay? It could be a limiting factor on each side. But anyway, so I don't see any TCP window size of 0, which means this is not TCP gating that factor. So what's the other way to look at it? How do you know, and this is actually, this one you want to remember, because this one you can remember and use and look like a hero when you're troubleshooting, which is exactly what you said. How do you know if it's application doing it or the network doing it? And in a lot of transfer use cases, push bit comes involved. So there's a 30-minute video that I did on what a push bit means, because it's more than just one thing. But in this session, push bit is the application saying, hey, TCP, I'm the sender. Okay? So if we look at this here, I'm 10, 10, 10, 10, 10. I'm sending all this data. Earlier in the first session, I said that TCP has no beginning and end. It's just a stream of data being sent through the pipe, which is the IP. So think of it again, for those of you that were not in the first session, think of it as a funnel with a bucket of water, and the bucket pours until the funnel is full, and then the bucket has to stop because you don't want to run over the funnel, and then the funnel drains it into TCP, okay? So the application says, listen, I'm not going to wait till I fill up the funnel, which is the TCP or the send buffer size. I'm going to give you chunks of data. So instead of giving you this giant bucket of water, I'm now going to give you a cup full of water at a time. I put the cup into the funnel, I wait for it to drain out, and then I get the acknowledgement that you got the entire cup, and then I give you the next cup. And when that happens, the push bit is set, almost always. Okay? When you flush the buffer to say, I'll give you the next buffer, next chunk, next chunk, next chunk, the push bit is set. So how do we see that? Push bit is in the TCP header. Okay? It is. So you can actually come over here and say, here's a trick that you can use. The flag, right? You can look at it down here, but you can also go right click and say, apply as a column. And then it shows up right here. Okay? So anytime it's just 10, that means he's just acking. Right? But when you see, if you scroll down here, and you see a different number than 10, like here, 18, that is push bit. So now I have a quick way of finding push bit to push bit, how much data are you sending me? And when you measure the push to push, you can tell how big the cup size is. Okay? Does that make sense? Because now, you can't do that with Telnet. You can't do that with interactive sessions. Why? Because everyone has a push bit on it. But when there's a transfer, a big clue is that when you see these large HTTP GET, for example, when you do the first GET, there's a push bit because you're saying, get this from me. And the server says, okay, that has a push bit because it's the end of a, so think of push bit as kind of like a sentence, a period at the end of the sentence. Okay? And then I'm going to give you a run-on sentence with a bunch of words, and then when I'm done, I put a period on it, which is a push bit. So push to push is a good indicator of this size, the cup size. Okay? And when I did this, it came out to about 64 bytes. 64,000 bytes. Surprise, surprise, surprise. That a lot of applications use 2048, 4096, 64K. Okay? What I mean by that is this application was only willing to send 64,000 bytes at a time. So my TCP window was much bigger, but the application was saying, got on a conference call and said, your application sucks. It's not the network. And he said, Hansang, what are you talking about? It's secure copy. Like, it's FTP. And I was like, uh-oh. Now what's the problem? And he says, my FTP doesn't have a buffer size. He goes, I've been to your class. My buffer size is big. And he was right. So then I said, well, who else could be at fault? So who's the middleman in this example? He's transferring a file through what mechanism? SSH. It's OpenSSH. Okay? So I did some Googling. I did some looking at it. And it turns out there's a channel session window size. And OpenSSH has its own buffering mechanism. So regardless of what the application wants to do, OpenSSH has a limit of like 4 times 64. So the older one is 64K. So after 64K, he says, I can't transfer anymore. I need to see an acknowledgement before I give you another 64K of buffer. Somewhat newer ones have 4 times 64K, and other ones have 64 times 64K. The only way to know is by fingerprinting it or by looking, it's OpenSSH. You can look at the source code, and there's in the headers.c file, you'll see channel session window, chan ses window, channel session window, okay? And that's the application buffer size that Secure Copy wants to use. So the long and the short of it is, from push bit to push bit, you can calculate how efficient and what the packet size is going to be. And you'll notice here, this is the end of the packet train, right? How do I know? Because this one doesn't have a push bit, but this one does. Another clue, it's not a full size. Almost a full size, but not a full size. Why? Because it was a little bit of a straggler, so 1460, and a little bit of straggler that was left over. In other words, I was giving you a full cup, full cup, full cup, and the last cup only has this much. So it's a little dribbler at the end. So what's the push bit to push bit? You can either calculate it by adding up from push bit, 0 by 18 to 0 by 18. You can kind of eyeball it. You can calculate it, or you can, in the newer TCP, under sequence number analysis, I think it is, you'll see bytes since last push. So Kerry Rogers, who works for Riverbed, added this in. Why? Because I always had to calculate this manually. And I went on a rant one time saying, it sucks that I have to do this. And Kerry's like, And I know how to code. It's been 30 years since I wrote code, okay? The last thing that I wrote was for my senior project is a 3-node network operating system. Outside of that, I don't know how to code anymore. So Kerry did this, and now you know. This is a good way of finding out how many bytes since last push flag. And you can see here it's 65K, 64K times 1024. Okay? Any questions on that? So this is a good thing to have in your column so that you can quickly see, instead of doing this TCP flag, you can actually make this a column as well, and then you can edit this guy column.
The pattern what we saw in the graphs.
That's exactly what you saw in the graph.
Yeah.
That's exactly what you saw in the column.
What we saw was is this the pattern of the push bits or the combination acknowledge and push bits? Because you had a different length of the size of the line sending the data.
So I'm sorry, I was editing this. What was the question again? I'm sorry?
The pattern what we saw in the graph,
Mm-hmm.
we had the different sizes of the length.
Yes. So why was that instead of this? Because remember, when I said that channel session window size, there's a multiplier effect. So it's 4 times this much, or sometimes the application is done sending you and has to open up a new file. So there's a discrepancy of, but you'll see a pattern of, 64, 64, 64, some straggler because I'm finishing up and I'm getting the next file to send over to you. And that file may not be as big.
Sometimes it was the session channel size.
Yep.
Sometimes it was the application.
That's right. So this is why you have to work with the application people, but this is another way of proving that you are not the bottleneck. Okay? However, and this actually happened. I used to teach this at Citigroup where I used to work, and I did these classes quite a bit, and one of the Unix administrators attended the class about, you can only transfer 1 round trip per window, and et cetera, and he said, oh, you know what, I'm gonna make my window size like 2 million. And then that morning his server crashed. Because thousands of people connecting to the server requires twice the receive window size. Why? You have to do receive window size and send window size. They go hand in hand. So if you make the receive window size 2 million, you need to have a send window size of 2 million by default. That's 4 million bytes per socket times thousands of users connecting to it. You quickly run out of memory. And that's exactly what happened. Okay? So dosage makes the poison. Too much of a good thing is a bad thing. So what should you do? What's the right answer? The right answer is work with the application folks. You know how big your backbone is, and you can give her a amount of data that's safe so that you, for example, how much data do you have to transfer? 100 gigs. Okay, how much time do you have to transfer that by? And you can come out with a reasonable window size that meets that criteria. What if they have more data than you have bandwidth for? Then what are you going to do? So in other words, he says, I got a terabyte and I need to do it in 4 hours, and you have a 1 gig network. What are you going to do? You're going to buy a steelhead, of course. Commercial number 3. Or order a bigger circuit. Okay? But if you order a bigger circuit, then it's going to take a little bit of time. Okay? So in other words, it's a simple math. Sit down on an Excel spreadsheet and figure this out. You have 100 gigabytes of data. You have 1 gigabit network. How long does it take to transfer that if you have complete wire rate of 1 gigabits per second? It's a simple calculation. You can't give that one application a gigabit of bandwidth because he'll chew up entire bandwidth. So reduce it by 300 megabits. So you have 700 megabits left over for other, et cetera, et cetera. Does that make sense? Okay. I've actually had to get down to that level of granularity, but it starts with how much data do you have, how fast do you need to transfer it by, and then I'll give you a reasonable window size to do it in. Okay? But after the TCP window size, you have to worry about the application buffer size. And that's where the push bit, the byte since last push bit, is the next bottleneck that application guys have to overcome. okay? There are multiple bottlenecks at play here. First one, TCP. That's easy. Open up a socket with a bigger window size. Application have complete control over that. It can override what the server default setting is when you open up a socket. So the application guys go, oh, I know how to do that. It's a set sock option. I'll open up a bigger window size. But the second one is the application, push to push, how much are you willing to send? That's the second bottleneck. Okay? Any questions on that so far? I only have 12 minutes, don't I? Jeez. Okay. Earlier I showed you this, so I'm going to just do it real quick. Earlier in the first session I showed you this where there was a delay between, delayed acknowledgement, right? And when I sorted by the delta here, you saw all these horrific delays of 200 milliseconds. This was all delayed ACK, okay? So I'll just give you the answer. The reason why this occurred was if I stop and analyze this, the problem is that this behavior is very non-deterministic. Every once in a while, the acknowledgement is for 3 packets, 4 packets, 5 packets, 2 packets. And I said, this can't be right. I'm capturing at the guy who's sending the acknowledgement, and I know for a fact that you're acknowledging every 3, 4, 5, 6, what the hell's going on? And this was the TCP offload engine trying to reduce the overhead of the interrupt of generating these acknowledgements, and it's called interrupt coalescence on a driver level, and it was non-deterministic. The problem is, if you do it 3 packets, then what happens to the 4th packet that just arrived? So let's say, make it easy, I'm going to send you 4 packets. The rule was, every 2, I acknowledge. So I get the 2, I acknowledge, I get the 2, I acknowledge, we move the line, keep the line moving. But the interrupt coalescence says, oh, I'm going to save you some time here, and I'm going to group 3 packets worth of data, and I sent an acknowledgement. What happens when that 4th packet comes in? It's only 1 packet. I can't send you an acknowledgement. I have to wait for delayed acknowledgement. So this delay kept happening over and over and over and over and over and over. So the first thing I did was, hey, how much data do you have to transfer? I'll give you the exact window MSS size that you need to be 100% even. Even then there was a problem because this interrupt coalescence. But when we fixed it, and I click on the delta time delayed here, you notice everything is, this is the worst case scenario. So every once in a while, there was 100, a few here, but these are more application level, giving the next set of transfer, next set of transfer, next set of transfer. Earlier, you saw thousands of 200 or more millisecond delay. Okay, that's delayed acknowledgement. This one, when we turned off that interrupt coalescence, it did every 2 packets act like clockwork. It was much, much faster. Okay, does that make sense? All right, so look up, especially if you're because you're paying a needless penalty and an undeterministic penalty because of interrupt coalescence on the network card. And when we got Intel driver people on the call, because I work for a very big company, you can do that, they said, yeah, we gave it a shot and it's probably a bad idea. And I said, that's your answer? So anyway, we made a point of turning it off, okay? So be on the lookout for that. Now, let's look at another issue. This one was a big one. 22,000 users logging in to their homepage. And just constant calls of slowness. Constant. So the first thing you rule out is black holing. Remember that 22,000 branch users going to one homepage across, 10 or 16 different head-end routers. That's still a lot of people per 10 or 12 head-end routers, right? 22,000 users, and this is their home page. Every time they open up their browser, it goes to the home page. Not uncommon in a corporate network. So the first thing I looked for was ICMP packets. And the 3.4, it wasn't the use case of ICMP type 3 code 4 where the router was eating up the path MTU discovery, okay? And if you scroll down here, it's 1460, et cetera, okay, full-size packets. But you do see here retransmissions, okay? So the two clients, I cheated here. I wrote down the client's IP address so I don't have to go looking for it. Here we go. So here's one person that didn't seem to have a problem. IP.adder equal 10.2.53.102. And we can see here sin, synac, act, data, let me get rid of this. Continuation, and then fin, finac, act, okay? Took no time at all. You guys see that? Sin, synac, and the page came up and took almost no time at all. This person had no issues. So I said, okay, well, it's not the network because everything is working as this. So then I said, let's take a look at, give me an example of a person that did have a problem. And they said, we got a lot of them. Here's an example, 10.17.9.7. So they're on a completely different network, completely different branch, and doesn't even exist. How about that? That's your first problem. Here's an example of the sin, and then immediately reset. What the hell is that about? Sin, I acknowledge the segment that I was unseen, and then I get a reset, and then a retransmission. I sent you a sin, and then you sent me a reset. Immediately I said, oh, the server's too busy. Server's too busy. And the server guy's like, what are you talking about? I sent you a sin, and you immediately reset me. It's your problem. And I said, not my problem. There's a load balancer in the middle. I'm not talking to the server, I'm talking to the load balancer, right? And I was like, oh yeah, of course. The load balancer is the problem. And the load balancer is like, dude, there's no CPU issue, there's no issues. And I'm like, another use case of nobody's problem, but nothing's working. The perfect saying for that, by the way, and you feel free to use this, I saw it on a poster, no snowflake feels responsible for the avalanche. And it's like a mantra for me these days, right? No snowflake feels responsible for the avalanche. So the big IP guy's like, I'm telling you, I don't have much utilization. There's nothing wrong with it. And I said, but then something caught my eye. And this comes with experience, okay? Let me go back to the other trace file. And the client was what? 53.102 was it? Yep. And then because of, remember there's more art than science, I said, oh, I think I know what the problem is. This is all it took for me to say, oh, I know what the problem is, potentially. I had to rule it out, but by doing just this, I said, big problem. Let me look at it again. So just kind of visualize this, just kind of soak it in. Let me get rid of the flags for you, because let me bring up the other trace file. Besides the reset, of course the reset's the problem. Reset's telling me, get the hell out of here. That's what reset is doing. But this is this is the load balancer telling me it wasn't a manufacturer big IP. Don't sue me. It was a load balancer. I'll edit that out. So it was load balancer that reset the connection. So clearly it's not the client browser. Remember I told you Internet Explorer resets connections by sending a reset? This is the load balancer sending me the reset. Completely different story. When a server sends you a reset, there's a problem. Usually it's because he ran out of sockets. Usually because he doesn't have enough connection table to open up another socket. This example is what? What are some of the things that immediately jump out at you? Look at the acknowledgement number there. What the hell? This is a relative sequence number, but still, like, where does that come from? Like, what? And retransmission, like what? I just sent you a SYN and you're telling me retransmission? Like, what's that about? You actually can retransmit a SYN, by the way, because SYN is the only non-data packet that sequence number goes up. Okay, SYN is the only packet in the FIN. The handshake is the only time when, even though there's no data, the sequence number has to go up. It has to do that because it has to track whether that got lost or not. If you don't send any data, you can't track whether it got lost again, remember? So anyway, if you're confused about that, read up on it or ask me in the hallway somewhere and I'll explain it in more detail. So the other thing that you notice right away here is what? Look at the port number. 3503. Ephemeral source port 3503 going to load balancer 443. Let's go back to the person that didn't have the problem, which was 102, I think. What number do you see there? 3503. Okay? So visually, because I'm out of time, I'm going to cheat by showing you visually what it looks like. Client 102 goes to the load balancer address of 10.10. That's what we saw in the trace file. And it gets natted to 20.20 and goes to the server, which is the actual application server, 172.16.254.254. We don't see this because we only see the front end connection here. And I'm opening up a connection on 3503 and 443. What did this guy open up on? 3503, 443. We both opened it up on the same ephemeral port and destination of 443. The load balancer should have done what? Besides opening up 3503 and 443, 3503, 443. Look at this back-end conversation from the server's perspective. The tuple is what makes it unique. Source destination IP, source destination socket is what makes it a unique connection. If you look at it from the source, 172.16.2020, source port 3503, destination 254.254, destination port 443. This is identical to this connection. So what's happening is the client traffic here from one branch and this client from this other branch at the server side looks like the same connection. So in the middle of the conversation, you're sending me some random sequence number, because the initial sequence number is random, and then you just add to it, okay? In the real world, the sequence number is not 0, it doesn't start with 1, it's a 32-bit number. So if I go change my profile to real sequence number, you can see why, I don't use real sequence numbers, because it's a pain to memorize these big-ass numbers. Okay? That's why Wireshark defaults to using, you know what, it's a relative, starting from this point, I'm going to add on additive bytes. Let me just start at 0. Makes it much easier. But this is the problem where the sequence number was being munged by the load balancer, failing to do what? Failing to randomize this back-end conversation. He shouldn't use the same 3503. He should randomize this so that these two conversations on the back end can be unique, okay? So initially what was happening, again, this conversation is going fine. Somebody all of a sudden jumps on to the home page and the server doesn't know if the conversation is happening here or if the conversation is happening here. So all of a sudden this guy's like, I'm done, but he still thinks it's this conversation. He sends a sequence number here saying, hey, we were talking at sequence number of like 4 million or so, 2 million or so, and all of a sudden you're starting out at 1 million? Like what the hell? Reset. Yes?
You might also have ran out of ports. Because if there's, you said 200,000 clients.
Okay, so that's a perfect example of, let's expand on that. If the load balancer ran out of SNAT table, there's only so many port numbers you can use, right? What would have been the symptom? A reset. What I would not see is a random sequence number that changes, okay? Does that make sense? So in other words, the point was, if this guy is servicing so many people going to the same server, I only have so many socket numbers I can use. If I run out of that, the next person that wants to connect, I say, sorry, see you later. But you would not see the sequence number being munged that you do, okay? And if you look at, I distilled it so that you can see it easier, where I just looked at the handshake, and you can see that there's some traffic happening here, some connection was happening, and all of a sudden the SYN happens, and Wireshark says, hey, by the way, you're reusing this port number probably not a good thing. So Wireshark is giving you metadata that the port number is being reused, and he says, what's going on, reset. And this is where, if you do the sequence number analysis, you'll see that the two sequence numbers are getting confused. Okay? But this is one case where you have to use real sequence numbers to see it positively. So the times that you want to use real sequence number instead of relative is when you have load balancers and when you're looking at two sides of a firewall conversation. So if you have a TCP proxy, you should use real sequence numbers, because otherwise you get lulled into thinking it's the same, and it's not. When you do a relative sequence number, it always starts from 0. So you want to use real sequence numbers to see the behavior of reply and ACK numbers happening. Clean side, dirty side of a proxy, clean side, dirty side of a firewall. So you should have a profile here to look at real sequence numbers. Yes, question?
Another question, what happens if you reach the maximum sequence number?
Okay, so the question is, it's a 32-bit number, right? So after 32-bit number is like what, 4 billion, whatever, it wraps around. That's a problem on a 10 gig network. If you do the math, on a 10 gig number, between the lifetime of that TCP session and retransmission timeout numbers, you can actually wrap around that sequence number. So there's another add-on to TCP called PAWS, Protection Against Wraparound Sequence Number. So they use a scaling model to make that sequence number much, much bigger than the 32-bit number represents. Okay, it's the same thing as like Windows scaling. Okay? Good question, great question. I ran out of time again to dedicate for a Q&A session, and if you see here, my stomach was bigger than my mouth or whatever, because I had a lot more trace file here. This one was really, really interesting one that I never got to, so I apologize for that. But maybe I'll blog about it or, put it on YouTube page, because that one I can spend 45 minutes analyzing, so I don't know what the hell I was thinking that I could get to it. But be that as it may, next up is lunch. But I'm going to stop the trace file, the recording here, and I'll answer any questions that you guys might have.